The purpose of doping a semiconductor is to add charge carriers, electrons or holes. You can dope it in such a way that either electrons or holes are added, or you can dope it such that both are added. I have the band diagram for an intrinsic semiconductor shown here, where the Fermi energy is very close to halfway between the valence and the conduction band edges. Now, if I add impurities to the semiconductor such that holes are added, what happens is that the Fermi energy is shifted relative to the band edges. Or you could say the band edges are shifted relative to the Fermi energy. We don't distinguish between those two statements because we're only able to use differences in energy in all of semiconductor physics. That's acceptor doped. So you add impurities which contribute holes, and the effect then is to pull the Fermi energy towards the valence band edge. If you add impurities that contribute electrons, the opposite happens. The Fermi energy gets pulled near the conduction band edge. So those two types are then referred to as either acceptor doped or p-type if you create holes, or donor doped or n-type if you create electrons. Those terms will be used interchangeably. Acceptor doped and p-type are used interchangeably. So that's what dopants do. They move the Fermi energy relative to the band edge. And I'd also mention that doping does not affect the gap size to first order. If you dope enough, it will. But we will go on the assumption when we dope our semiconductors that the gap is not changing. So we have this expression for the carrier density that we derived last time. In case of electron carriers, it's as this n sub c, which is the effective density of states, times this exponential, where the energy in the exponential is the difference between the conduction band edge and the Fermi energy. And n sub c comes from table 1.4. So what happens when you dope? Which came first, the chicken or the egg? You change carrier concentration because the Fermi energy moved relative to the conduction band edge. Or the conduction band edge and Fermi energy got closer because you changed carrier concentration. But if you donor dope, N increases, and if you acceptor dope, P increases. Those are the carrier concentrations. Let's take a look at a specific semiconductor, germanium. It's a group 4 element. We can dope it several ways. First, if we dope germanium with group 5 dopants, there will be N-type because group 5 elements have one extra electron than group 4 elements. When a group 5 element substitutes a germanium atom, there's an electron that can come loose and join the conduction band. Common examples, phosphorus, arsenic, and antimony. And so how do you do it? You get the phosphorus, arsenic, or antimony to diffuse throughout the germanium, which you will do quickly during annealing, that is, during an elevated temperature stage of the preparation. Usually what happens, first, the most favorable thing is for a dopant to replace a vacancy. The semiconductor material, pure germanium, is full of point defects, and those vacancies get filled, and the dopants hop from vacancy to vacancy until finally they have diffused all the way through the semiconductor. If you wanted to make a p-type semiconductor, you would use group 3 dopants, boron, aluminum, gallium, and indium. In group 3, there are fewer electrons, and so those impurities will accept an electron. They look for an electron. Well, they're not going to find an electron in the conduction band because there aren't very many. So they're going to steal electrons away from other germanium atoms. They're going to create holes. We call it acceptor dopants because they accept electrons. As a result, you end up with a hole in the valence band. You can make it during the fabrication process by diffusing those group 3 elements. They diffuse more slowly, but you can still introduce them slowly by diffusion. But something else that's used a lot to make p-type dopants, that is put boron and germanium especially, is ion implantation. And we will talk about that in chapter 3 a little bit. An ion beam is used to place dopants at desired depths into the material. This is a fairly quick example. If I take some germanium and I dope it with a group 5 element, so phosphorus, for example, with N sub D, that is the dopant concentration or you call it the donor density. Lots of things you can call N sub D, but it's the concentration of these dopants with phosphorus, arsenic, antimony is 10 to the 16th per cubic centimeter. I want to know how much the Fermi energy moves. So what is the distance now between the conduction band edge and the Fermi energy? And we'll do this at 290 Kelvin. You'll notice a slight distinction in the value of KT. We look up germanium in table 1-4 in the book, and we find that N sub C is that 1.04 times 10 to the 19th per cubic centimeter. I'm going to use the complete ionization approximation. At room temperature, it is fairly safe to assume that all of the dopant atoms have ionized. So if they're donating an electron to the conduction band, they've all done it. If they're accepting an electron from the valence band and creating a hole, they've all done it by room temperature. Doping puts the Fermi energy much closer to the band edge. And at room temperature, ionization is a sure bet if you have high enough doping density. So we're going with the complete ionization approximation. That is, we will say that the charge carrier density, little n, is equal to the donor density, the density of impurities that have been doped into the semiconductor. So if I put 10 to the 14 impurities per cubic centimeter of semiconductor, I'll have 10 to the 14 electrons per cubic centimeter. This is true as long as the dopant density is significantly greater than the intrinsic carrier density, which is what we're actually going to talk about next. So hang on to that question mark there for a page here. So let's do a calculation. We will use 10 to the 16th for little n. 1.04 times 10 to the 19th comes out table 1-4. And let's calculate EC minus EF. Now I use 0.025 instead of 0.026 for KT because the question said at 290 Kelvin. And you end up with the conduction band edge and the Fermi energy being 0.174 EV apart. So what does that mean? The band gap for germanium is 0.67 electron volts, which is a lot bigger than that. And so if I sketched the band diagram now for this doped germanium, it would look like this, where the Fermi energy is shifted until it is 0.174 electron volts below the conduction band edge. It's always below. If the Fermi energy is above it, what's called degenerate semiconductor, it is possible to send that Fermi energy into the conduction band, at which point the semiconductor starts to behave like a metal. Okay, there's an example. We just calculated the new Fermi energy location based on doping density in germanium. So let's go a little bit farther with this calculation. Even though it wasn't in the problem statement, let me ask you one more question. What is the hole concentration, P, in this problem? It's a donor-doped semiconductor. It contributes electrons to the conduction band. But nevertheless, we can check what the hole density in the valence band is by using our expression that we now have. Now we use N sub V from table 1-4, 6 times 10 to the 18th. We just figured out what E Fermi minus E valence is. It's 0.496 EV. Don't believe me? Go back and look. 0.496 is that difference right there from E Fermi down to E valence. So use that for E Fermi minus E valence. And go ahead and calculate a hole density of 1.45 times 10 to the 10th per cubic centimeter. So it's a lot less, right? There are a lot more electrons. What do we have? We had 10 to the 19th electrons per cubic centimeter. We have 10 to the, so 9 orders of magnitude fewer holes and electrons. But it's worth checking. And the reason why is I want to make a point to you that there's a trade-off between N and P in equilibrium. If you increase the number of electrons, you will decrease the number of holes and vice versa, such that the product of N times P, the product of the electron concentration times the hole concentration, is a constant. Square root of NP is N sub I, the intrinsic carrier concentration. The intrinsic carrier concentration is roughly the concentration of electrons that semiconducting material has when it's intrinsic, when it's undoped. In fact, we'll say in the event that the semiconductor is intrinsic, the hole density and the electron density are supposed to be equal, and they're equal to N sub I. Now, I put those approximately equal to signs in there because, as we have established last time, Fermi energy is not dead center in the gap. And so actually, even in the intrinsic semiconductor, N and P are not exactly the same. But roughly speaking, N and P and N sub I are all going to be the same number for an intrinsic semiconductor. In this course, we're going to treat it that way. We're going to treat the square root of NP as equal to this N sub I. And let's calculate what that would be for germanium. And to take to heart the statement down here that this product, NP, is a constant. If you change the doping, that constant does not change. So let's calculate this intrinsic carrier concentration. In general first, let's get an expression. I will take the square root of NP and use these equations from most important equations in the book, 185 and 188, insert them in for N and P, and you have this expression for the intrinsic carrier concentration. I would like to clean that up a little bit. Let's simplify the exponents. Do you see how E Fermi is going to go away? So let's go ahead and do that, make that go away. In fact, you can clean it up a little bit more. E conduction minus E valence, that's the gap energy. And that's usually the thing you look up. You don't care what E conduction as an absolute value is. You care what the difference between E sub C and E sub V is. So let's put the E gap in there. I brought the 2 upstairs just because that's the way everybody writes this expression, with the 2 like that instead of down there. We have the intrinsic carrier concentration of a semiconductor. It's approximately equal to N and P in the intrinsic case. Let's go back then to the germanium example and put in some numbers. So we have NC and NV from the table in the book, and an energy gap also comes from a table in the book. Look them up in those tables, plug it in, and we calculate, remembering that KT at room temperature is 0.025 EV, KT at 290 Kelvin. So we get an intrinsic carrier concentration for germanium of 1.2 times 10 to the 13th per cubic centimeter. Can't emphasize enough that that is independent of doping level. That's going to be the square root of the product of N and P, no matter how much you dope it. Doping is only useful if you dope to a greater concentration than N sub I. If I had 10 to the 9th per cubic centimeter dopants, there would be no impact on the carrier concentration. If you're going to dope germanium, you're going to put more than 1.2 times 10 to the 13th dopants per cubic centimeter in order to contribute a significant number of carriers. You'll probably dope to 10 to the 15 or 10 to the 16 typical doping levels. I'll stop with that. We'll do an example, problem 1.11 from the textbook next.